So wait.
Yeah, it is live now.
It's live. Okay, very good. Thank you everyone for joining today. I'm sharing my screen. You must be able to see my slides now. Okay. Okay, yeah, thank you, Geraldo. Hello, everyone. Welcome, and thank you for joining this second lecture of our P&S on processing in memory. Today, we are going to talk about real-world processing in memory architectures, and in particular, we are going to focus on the microarchitecture and the ISA of the UPMEM PIM architecture. There have been like very good news in recent times for computer architecture, I believe. So in sometime in 2016, UPMEM, which is a French startup that was founded in January 2015, announced the first real-world processing in memory architectures. After that, they started to develop their architecture, their product, and sometime in 2019 or beginning of 2020, I'm not exactly sure, they started to commercialize it. Here on the right-hand side, you can see some news from those times, right? This is already 5 years old. The interesting thing is that UPMEM is not the only company that is working on processing in memory and pushing for it. We also have Samsung, as I mentioned in our previous meeting. In early 2021, Samsung announced the FIMDRAM architecture in ISSCC conference. And sometime later this year, also announced the LPDDR5 version and also the AXDIM architecture that is built on DDR5 DRAM memory. So definitely something is happening in computer architecture, and we are close to start solving the real issue that we have in computing systems. In the previous slide, I showed you this piece of news from 2016. This is the announcement from Samsung in February this year, the new processing in memory architecture for AI that places computing capabilities inside the memory layers of the HBM2 memory. And this is the UPMEM processing in DRAM engine or processing in memory engine that I already presented and mentioned in the previous lecture, and we are going to focus on this architecture today. Recall that the UPMEM-based PIM system consists of a CPU that is connected to a number of DDR4 DIMMs and also a number of DDR4 PIM-enabled DIMMs, which are the UPMEM DIMMs that you can see in the picture. Regarding Samsung, let me remind you what the FIMDRAM architecture consists of. It's composed by multiple layers, as in the typical HBM stack, HBM2 stack. But here we distinguish between two types of layers. There are layers that are pure storage, as these 4 on the top, and then there are other layers that are compute capable. Those are the FIMDRAM layers, as you can see on the slide. And here in the next slide, you probably saw this picture, this slide already in the last meeting. It's where we see the layout of one of these layers where we can find one of these PCU blocks, which are the processing unit next to two banks, bank 0 and bank 1. And then, as I presented also the other day, and I just mentioned as well, is a DDR5 PIM version that has been tested for DLRM recommendation systems and consists of, I mean, it's essentially one DIMM consisting of multiple DDR5 DIMMs, chips, sorry, and then this AXDIMM buffer. Okay, but today we are going to focus on the microarchitecture and ISA of the UPMEM PIM architecture. These are 2 sample DIMMs. Actually, this consists of the first generation of the UPMEM DIMMs. It's E19, consisting of 16 chips per DIMM. 8 chips per DIMM. These 8 chips compose what is called one rank. It's essentially what you can see in the picture. And here inside each of these chips, there are 8 DPUs, each of them with its own DRAM subarray or DRAM bank. And these DPUs run at the frequency of 267 megahertz. More recently, a new generation of UPMEM DIMMs, now consisting of 16 chips, so 2 ranks on each DIMM, and the DPUs are a little bit faster, running at a frequency of 350 megahertz. These values of frequency are expected to increase a little bit, maybe until 400, 450 megahertz, as far as we know. So processing in memory, as you already know, promises a nice way of alleviating the data movement bottleneck. The other day in the presentation of this course, I showed a slide from Bill Daly, where we could see a comparison between the amount of energy that is spent on accessing one cache line from memory and the amount of energy to execute one double precision addition in the core. And we saw that there was a difference of 2-3 orders of magnitude in terms of energy consumption. I think we have very similar numbers also in this slide, which comes from the UPMEM's presentation at Hot Chips 31, as you can see in the slide. And here you can compare these 2 numbers, DRAM to processor 64-bit operand. So how much energy we need to spend to bring some operand from DRAM to the processor. So in case of a normal DRAM system, a normal system with a server or a CPU and normal DRAM, we are in the range of 3,000 picojoules. If we compute near the memory, near the bank in one DPU, this gets reduced by 20 times, as you can see on the slide. So definitely very promising numbers, and I think that this is, I mean, it's like a very first thing to show, to try to convince everyone that processing in memory is definitely here to stay. But it has not been easy, for sure. I remember I mentioned in our previous lecture, I mentioned that processing in memory was originally proposed in the early 70s or the late 60s, but by that time and even later, it wasn't possible to integrate these kind of devices in real systems because of certain technology constraints, technological challenges, let's say. And here you have some of these, right? Some of the hurdles or some of the issues that UPMEM folks had to face when they started to develop their UPMEM PIM architecture. Because these DRAM processing units are inside the DRAM chips, they are built using the DRAM process. And the problem with the DRAM process is that transistors are much slower than in an ASIC process. And also the circuitry cannot be so dense, and you cannot have so many metal layers, for example. So this makes that building an efficient and fast processor inside DRAM is so difficult, right? And this is for sure imposing some limitations in the design of the DPU, of the DRAM processing unit, as we will see. But still, it's worth it, as the slide says. Actually, UPMEM and Fabrice Deveau, who is one of the inventors and CTO of UPMEM, filed this patent in 2019, where they describe exactly what their system is. And I like to read the abstract or highlight a couple of sentences or elements in the abstract, because they clearly explain and reflect what this UPMEM PIM architecture is about. So UPMEM consists of, or UPMEM PIM architecture consists of a memory circuit having a memory array and something that here is called a first processor, and this first processor is the DPU, the DRAM processing unit, and a control interface. This control interface is for the central processor. It's a CPU that we are going to call the host CPU in this lecture. For this central processor to access the memory array, we have this control interface. And the memory banks become accessible to the central processor when they are not in use by the first processor. So that's essentially what we can see in the UPMEM PIM architecture. It essentially follows what we call the accelerator model. In the accelerator model, the UPMEM DIMMs coexist with conventional DRAM DIMMs, and the UPMEM DIMMs can be seen as a loosely coupled accelerator. In this model, we need to explicitly move data between the main processor, the host CPU, or the central processor, as it was called in the abstract of the patent, and the accelerator, which are the UPMEM DIMMs, right? And then after this data, input data, has been moved to the memory of the accelerator, we can explicitly launch the kernel onto the UPMEM processors for the processing in memory execution. And so this model resembles GPU computing. Probably many of you are familiar with GPU computing. This slide comes from one of our lectures on GPU computing. When we are working with discrete GPUs, what we typically do is, first of all, we transfer from CPU memory to GPU memory the input data, for example, a matrix. Then we perform the computation using the GPU cores and accessing data from the GPU memory. And after the computation is done, we need to move back the results from the GPU memory to the CPU memory. So this is what the accelerator model consists of. Here it's applied to the GPU computing, the classical model, when you have a CPU and a discrete GPU. If you want to learn more about GPU computing, I would recommend you this lecture that I gave like 2 or 3 years ago about GPU programming, but also I would also recommend you this another P&S that we are teaching this semester on hands-on acceleration on heterogeneous computing systems. Okay, but let's go back to the UPMEM PIM system. Oh, by the way, one thing that I would like to clarify up front, because maybe some of you are thinking, okay, what's the difference between an UPMEM PIM system and a heterogeneous system with a GPU? As I said, the accelerator model is exactly the same, but then there are some differences. So one first difference is that the UPMEM PIM system typically provides much larger memory capacity. I can tell you that current UPMEM PIM systems, as the one we are going to start describing and analyzing today, has around 160 gigabytes, which is at least 4 times more than current GPUs and the most powerful GPUs. Another key difference is that in the GPU, we have a single memory space, right? While the UPMEM PIM system is more like a distributed system. Okay, so I wanted to very quickly clarify some of the differences between them. But anyway, we will continue talking about them. At some point, we will present some results comparing performance and energy consumption in an UPMEM PIM system and a GPU, and you will see, we will continue describing the differences and probably when it's preferred one type of accelerator over the other one. Okay, going back to the accelerator model and going back to the patent, this figure that you see on the slide is also coming from it. It's figure 6 in the patent, and this presents a flow diagram describing the operations when we want to offload or delegate some computation onto the DRAM processor, onto the DPUs or DRAM processing units. So in the first step, we'll have the SoC, the host CPU, loading data to be processed to the DRAM memory bank. And then the SoC or the host CPU transmits data processing command to the DRAM processor. So this is when we launch the kernel for execution on the DPUs. And after that, the data starts being processed by the DPUs, by the DRAM processors. In the meantime, the CPU is waiting. So far, this UPMEM PIN system that doesn't support, let's say, concurrent access to the memory banks from both the DPU and the host processor at the same time. So that's not possible. So what the CPU is doing is checking when the DPUs finish the execution. And then at some point, the bank, when the execution on the DPUs, on the DRAM processing units finish, the bank gets accessible by the SoC, by the host CPU. So this is how it works. And then at that point, the CPU can retrieve the final results. Okay, so here you have one more slide, one more figure from the patent that also describes pretty well what's the system organization. You can identify here the SoC or the host CPU. You can see here the UPMEM chips, the PIM chips, and then inside them we have memory arrays, and we have the processors, these small green rectangles that you can see on the slide. As I said before, in the UPMEM-based PIN system, UPMEM DIMMs coexist with regular DDR4 DIMMs. We have typically something like this. As you can see in the figure, we have the host CPU, and this host CPU is connected via memory channels to the main memory, which are DDR4 DIMMs or in general, conventional DRAM DIMMs. And then we have a number of PIM-enabled DIMMs that contain these PIN chips. So, as I said before, on each UPMEM DIMM, we find 8 or 16 chips. So this means 1 or 2 ranks of 8 chips each. And inside each PIN chip, what we find are the memory banks themselves, typically 8 memory banks of 64 megabytes. And we call these memory banks main RAM or MRAM. And then we have 8 DRAM processing units or DPUs in each chip. So we have 64 DPUs per rank. Also, as you can see in the figure, the internals of the PIN chip, you can see these kind of 8 slices corresponding to the 8 memory banks and the 8 DRAM processing units that are connected to them. And in each of these slices, we have the 64 megabyte DRAM bank, which is called MRAM, as I said. And then we have the an in-order pipeline. We are going to talk about this one a little bit more in detail in a few slides. And then in between, there are 2 types of memories. These are SRAM memories. One of them is an IRAM, an instruction memory of the size 24 kilobytes, and the other one is a so-called WRAM or working RAM, which is a kind of a scratchpad for input and output data, input and output operands that are going to be used by the pipeline. And this WRAM is of size 64 kilobytes, as you can see on the slide. Both SRAM memories are connected to the MRAM bank using a DMA engine with as you can see here, there's an internal bus of 64 bits, and this DMA engine can move instructions from the MRAM bank to the IRAM. The size of the IRAM, as I said, and as you can see on the screen, is 24 kilobytes. This is, if I recall correctly, is up to 4,096 instructions. and similarly, the DMA engine can move input operands from MRAM to WRAM or output operands from WRAM to MRAM when the computation finishes in the pipeline. One typical configuration these days for the UPMEM-based PIM system, it's a dual socket CPU containing 20 UPMEM DIMMs of 16 chips each. So in total, we have 40 ranks. So 40 ranks means up to 2,560 DPUs in the system. And here on the right-hand side, you can see a picture that kind of represents this UPMEM-based PIN system. So with 2,500 up to 2,560 DPUs and up to 160 gigabytes of memory. It's actually the number that I mentioned a few slides ago. And here you can see a nicer picture of the system, the internals of the system, where we can identify the two CPUs, CPU 0 and CPU 1. Then we can also see some DIMMs of DDR memory, which is also DDR4 memory, which is the main memory of both CPU 0 and CPU 1. In particular, there are 2 DIMMs of DRAM per socket, and then we have a few DIMMs of PIM enabled memory. There are less powerful systems. Let's say we have also worked with this the smaller system with 640 DPUs. This is a single socket, and yeah, so it's a configuration similar to the one that you can see on the figure. It's up to 640 DPUs and up to 40 gigabytes of MRAM, of PIM enabled memory. Okay, so yeah, so very briefly about the DPU sharing, security implications, and so on, right? Because this is probably some question that someone may be asking themselves already. Is like, what if you have multiple processes running in the system, and these processes want to make use of the PIM capabilities, of the PIM processing elements? Well, one thing to say here is that DPUs cannot be shared across multiple CPU processes. One, let's say, rationale behind this decision is that there are so many DPUs in the system that instead of like time sharing these DPUs, it's better to assign different DPUs to different processes. That's something that programs could do, because programs can decide how many DPUs they are going to use, how many DPUs they want to allocate. So that's one thing that can be done. And the fact that these DPUs are not shared across processes makes things simpler, right? For example, there's no need for operating system that takes care of partitioning, like doing time sharing of the DPUs. And also there are simplified security implications. There are no side channels, right? Because you don't have 2 processes running at the same time on the same processor. So in that case, this is actually one advantage of this UPMEM-based PIM system. Okay, in our next lecture, we'll probably start talking about how to program the UPMEM-based PIM system. For now, what I just want to mention is I just want to very briefly introduce the way that we typically partition the computation among the available GPUs. So, and first programming example is vector addition. I cannot think about something simpler and better for a start. In vector addition, as probably you all know, what we do is an element-wise addition of 2 arrays, input arrays A and B, and we store the result in an array C. So the way to distribute this computation onto the DPUs of an UPMEM-based PIM system is by partitioning the input and the output arrays across DPUs, and then inside each of the DPUs. So here, as you can see, is a number of, so the arrays A and B, we are partitioning them in 4 pieces, assuming that we have 4 DPUs in our system, or we are going to make use of 4 DPUs. And then inside each of the DPUs, we have software threads running on the DPU. These software threads are called tasklets. Here in the figure, because this is like a pictorial representation, a toy example, we are just using 2 tasklets, tasklet 0 and tasklet 1 in DPU 0, in DPU 1, DPU 2, and DPU 3. 2 tasklets will be actually quite a low number of tasklets, as we will see. We will start talking about these today, but we will see even in more detail in our next lecture. We will see that the typical number of tasklets will be more than 11, and then 16 is a perfectly nice number to use inside each of the DPUs. Okay, and now that you are familiar with DPUs, or you already know what's a DPU, what are the components that the DPU has, and what are the threads running on the DPUs, these tasklets, I think we can go into more details. In the very beginning, and also, by the way, let me know if you have any questions. Don't hesitate to interrupt me if you have any questions. Okay, so as I said in the beginning, the UPMEM-based PIM system follows the accelerator model. In the accelerator model, we need to move the data from the main memory to the PIM-enabled memory. Then we perform the computation in the PIM-enabled memory using the DPUs. And finally, we will move back the results from the PIM-enabled memory to the main memory, right? This is the movement of data from main memory to the PIM-enabled memory is what we call CPU-DPU transfers. When we retrieve the results, we call that like DPU-CPU transfers, because we are going in the opposite direction. And we are not going to enter into the details in this lecture today, but I can tell you already that there are different ways of performing these transfers. It's possible to do serial transfers when we are targeting from memory, I mean, either from CPU to DPU or from DPU to CPU, but we are only using one single DPU, one single MRAM bank. So if we want to send data to multiple MRAM banks using serial transfers, we will have to go one by one. And then there is the possibility of doing parallel transfers, either CPU to DPU or DPU to CPU. And these can be launched in parallel, and we can transfer data from main memory to multiple MRAM banks at the same time, or vice versa. And finally, there are also, which as you will see in a future lecture, they are even faster, these broadcast CPU DPU transfers. But as I said, I don't want to enter the details of these types of data transfers. I'm only introducing them for you to understand how data is moved between the main memory and the PIM-enabled memory, and also to bring up something that is the inter-DPU communication, because this is a kind of a relative constraint on the UPMEM-based PIM system, is the fact that there is no direct communication channel between DPUs. And what this means is that all communication that needs to happen between DPUs, even if these DPUs are inside the same chip, should be through the host CPU, should be via the host CPU. So if, for example, we want to copy some data from this PIM chip to another PIM chip on the same DIMM or a different DIMM, what we will have to do is first copy the data to the main memory, and then from the main memory to the destination MRAM bank. Yeah, we will probably talk more about possible communication patterns. Some communication pattern might be like only merging partial results to obtain the final, so merging partial results to obtain the final result. This is, I don't know, for example, we have multiple DPUs computing different parts of a histogram or different subhistograms for different parts of the same image, and then at the very end, we move the subhistograms to the main memory, and then the CPU merges them and obtains the final histogram. This could be one example. Another example would be or a different communication pattern would be the redistribution of intermediate results for further computation. So it's like, for example, in iterative algorithms, when we obtain some intermediate results, and then we need to redistribute these intermediate results across the available processors, the DPUs in the systems, what we will have to do is bring all the intermediate results to the main memory, perform this redistribution from the host CPU, and then move data again to the MRAM banks to continue with the execution. Okay, so now, as you can see, this inter-DPU communication is going to entail some overhead, right? So it's something that it's already giving us some hints about what could be workloads that benefit more from this UPMEM-based PIM system, and what are the workloads that maybe will have more trouble when running on this architecture. But we will talk about that in a future lecture. For now, I prefer to focus on the microarchitecture of the DRAM processing unit and the ISA, the instruction set architecture that is used. If we look at the internals, and actually this is again from the patent, if we look at the internals of the DPUs inside each of these PIM chips, what we find is that, so we have the PIM chip, and then in the PIM chip there are a number of memory banks. We know already that this number is 8 in the current implementation, and then together with the memory bank, we also have like a pipeline, right? In this case is the DPU pipeline, and here you can see the instruction memory, the pipeline itself, and the local memory. We can see all these components in a little bit more detail. This is the figure that I showed you before. On the left, you have the host CPU, you have the main memory, and then you have the PIM-enabled memory. PIM-enabled memory is composed by multiple DIMMs, each of them with 8 or 16 chips. And these PIM chips are, yeah, so you can see the internals of the PIM chip here. We are gonna go one by one over the different components of this UPMEM PIM chip. So first of all, you can find this control and status interface and the DDR4 interface. These are for the host CPU to be able to access and communicate with the internals of the PIM chip. The DDR4 interface is for the host CPU to write and read data from the memory arrays, from these MRAM banks that we can see here. The control status interface has a double purpose, right? So the first one is to send the command for the kernel launch to the DPUs, and then also to check what's the status and check when the execution has been completed, has finished. Then we can find the 8 64 megabyte DRAM banks called MRAM or main RAM, as I said before. And as I also described, these, so the way of accessing this MRAM bank is using a DMA engine and this bus of 64 bits. And by using this DMA engine, we can either move instructions to the 24 kilobyte IRAM. This copy of instructions is usually transparent to the programmer. This is going to be handled by the runtime system. And then we have the working RAM, which is a scratchpad memory for input and output operands of size 64 kilobyte. And here the programmer can explicitly manage these copies between MRAM and WRAM and vice versa, right? This is a scratchpad. Let me remind you that a scratchpad is a software cache. It's not hardware managed, so it's a complete responsibility of the programmer to handle this WRAM in an efficient manner. And then we have the pipeline, including the register file. Let's very quickly, or let's quickly talk about this in order pipeline. As I said, in current UPMEM-based PIM systems, the DPUs can run at a frequency of up to 350 megahertz. And this is a fine-grained multi-threaded pipeline with up to 24 hardware threads. Before we go into describing each of the pipeline stages, let me very quickly remind you what a fine-grained multi-threaded architecture is. And actually, if you are interested on learning more about fine-grained multi-threading, I would recommend you one lecture from Professor Mudlum. The key idea in fine-grained multi-threading is that we have on the hardware, we have multiple thread contexts, and each of the thread contexts is defined by one program counter that, as you know, contains the address of the next instruction to be executed on the pipeline, and then a number of registers. So we have multiple thread contexts, and each thread context is one PC and a certain number of registers. So what the hardware is going to do is overcycle the hardware is fetching instructions from different threads and launching them onto the pipeline. And this way we can achieve what's the key idea in fine-grained multithreading, which is the latency hiding mechanism. The fact that we are issuing onto the pipeline instructions coming from different threads means that we have the ability to hide long latency operations from a certain thread by executing instructions of another thread, right? So for example, we may have thread 0 that at some point, after having execute some computation in the pipeline, needs to go to the main memory to bring some data and continue the execution, right? And usually these memory accesses, as you all know, are long latency operations, much longer latency operations than execution of, for example, arithmetic instructions on the pipeline, right? So while this thread 0 is accessing the main memory to bring some data, we can schedule other threads on the pipeline. And this way, we manage to hide the memory access by executing instructions on the pipeline. That's essentially the key idea of fine-grained multithreading. And these UPMEM DPUs are fine-grained multi-threaded processors. If you want to learn more about fine-grained multithreading, I would recommend you this lecture from Professor Mutlu in our Digital Design and Computer Architecture course. And here you have a couple more links to related lectures. Okay, so going back to the DPU pipeline, inside the DPU pipeline contains 14 pipeline stages. Some of these stages are different cycles, let's say, of the same stage. Like for example, fetch in the fetch stage, we have 3 cycles to read some data from some instruction from the IRAM and start decoding it. Then we have the read operand stages where we access the register file for input operands. And then where there are there is here one operand formatting stage. And then we have 4 stages for the ALU, our arithmetic and logic unit. Also, here, these 4 cycles, we can use them to execute arithmetic or logic operations, or to access input operands or output operands from the WRAM. And finally, the result formatting, these 2 merge stages that are to complete the execution of one instruction and write back to the register file. So in total, 14 pipeline stages. We will probably talk again about this in the next lecture. Okay, besides the DPU pipeline, now we know that the DPU pipeline is an in-order pipeline. It's fine-grained multi-threaded. It can run up to 24 hardware threads and has 14 pipeline stages. But what about the instructions that run on this pipeline? And this is defined by the DPU instruction set architecture. Is a specific 32-bit ISA aiming at the scalar, in-order, and multi-threaded implementation, as you already know. It allows for compilation of 64-bit C code by using their LLVM-based Clang compiler. Right, so here you can find a link to the SDK where you will find the manual, the documentation of the SDK, where you can find this section about the instruction set architecture. We may talk about these instructions in more detail in future lectures. For now, I just want to show a couple of examples, right, for you to see how these ISA instructions look like, and you will see that they are relatively simple and relatively easy to understand, but also like very nicely designed. So here you have some high-level language code on the top and some DPU code on the bottom. After this could be what is generated by the compiler after the compilation. This is one of the micro benchmarks that we have used in our work. I will probably show you in the next lecture a few results obtained with this micro benchmark. As I said, on the top, C-based code, on the bottom, compiled code. And here we can see instruction by instruction how they are compiled, right? So this is the for loop. So the for loop translates to this move instruction to initialize the index, and then we have the index update here in line 7, this add instruction, and this jump not equal is a conditional jump. What we are doing in this case is comparing the value of the index with the maximum size. In this case, size is 256. We compare if they are not equal, we jump here to this level in line 2. If not, we simply continue the execution because the loop has finished, right? And then here we have the access to WRAM. This buffer A is a buffer, an array we have in the working RAM, in the scratchpad memory, SRAM based scratchpad memory. Remember, we have previously allocated this buffer A in the WRAM using this memalloc. I'm not going to describe in detail what this means, but you can imagine this is an allocation of a certain size inside the WRAM. We will talk about this in more detail in a future lecture where we talk about programming the DRAM processing units. And yeah, so these read from buffer A translates or compiles to 2 instructions. In this case, in the first one, we calculate the address, and in the second one, we load from WRAM. And then we have this add instruction. We are adding 1 scalar to the value previously read from MRAM. So this compiles to this add instruction, and then we write the result to the buffer A again. So it's a SW is a store to WRAM, right? Okay, so this is some example code. We will probably talk more about this code and others in future lectures. And here you can see some more code. On the left-hand side, you have the C-base code. On the right-hand side, you can see the compiled code. And actually here we have 2 different micro benchmarks. The one on the top is essentially the same as the one of the top is essentially the same as you have seen in the previous slide. The one at the bottom corresponds to, it's the same micro benchmark, but it corresponds to 64-bit computation. So in this case, we are using integers. In this case, we are using long integers, right? And you can see that both compiled codes are pretty similar. The key difference is this add C, add with carry for the 64-bit computation, because registers inside the DPU pipeline are 32-bit. So if we are operating on 64-bit values, we need to use 2 registers per value. And after executing the addition for the lower bits of the 64-bit elements, then we obtain 1 carry, and we have to add this carry to the upper 32 bits of the 64-bit element. So if you count this for loop here translates or compiles to 6 instructions. This one here compiles to 7 instructions, and this is going to impose a small difference in performance for 32-bit and 64-bit computations, as we will probably see in our next lecture. Okay, yeah, we are almost done, I guess, with the description of the internals of the UPMEM DPUs and this introduction to the UPMEM PIM ISA or DPU ISA. Recall that inside each of the PIM chips, we have 8 of these slices. Each of them is composed by 1 MRAM bank, and connected to it or attached to it, we have 1 DPU, and the DPU consists of 1 in-order pipeline, multi-thread in-order pipeline, and 2 SRAM-based memories, 1 for instruction, the other one for operands, and we access these. So we either load instruction in the NRAM or move or load, read or write operands from this in this WRAM by using this DMA engine that connects the MRAM bank to the IRAM and the WRAM. In more detail, we will talk in our next lecture about the access from the pipeline to the working RAM. We will also talk about the access between the WRAM and the MRAM bank, we will see, or we will obtain some numbers for the latency and the bandwidth that we can achieve here. And finally, we will also see some results that compare the arithmetic throughput in the pipeline to the bandwidth of access to MRAM, right? So it's we will see some results for the arithmetic throughput versus the operational intensity. But this will happen in our next lecture. We will talk about the micro benchmarking of the UPMEM DPUs, or we will review some of the concepts that we just explained about the DPU microarchitecture and the ISA, and then I will show you some micro benchmarking results that will give you a very clear idea of what's the potential in terms of compute throughput and bandwidth of this architecture. In later lectures as well, we will talk about how to program the UPMEM-based PIM system, and in some way we will also introduce the Samsung PIM architectures and compare them to the UPMEM PIM architecture. I think that this kind of analysis is going to be quite interesting. I already mentioned this in our previous lecture, but if you are impatient and want to really go quickly and understand all these details very soon, you can already read our paper that it's available in archive, or watch this long talk that I gave 2 or 3 months ago. Okay, so this is all from my side regarding the lecture itself. Do you guys have any questions? Tobias, Lefket?
No, not currently, no.
Okay, that sounds good. Well, as you know, you can reach us in Moodle or email if you have any questions about what I just presented. It will be really nice to have some discussion with you about this. Now we are going to finish the lecture part of our meeting today. I would like to thank you, everyone attending the lecture in YouTube. I hope you find it interesting, and I hope you keep being interested about processing in memory, and in particular about the UPMEM PIM architecture. We will continue next Tuesday at 7 p.m. If you find, like, I don't know, you have any questions or want to reach for some discussion, feel free to send me an email. Thank you very much for your attention.